Okay, so how's it going? This is my paper, Unimodal Probability Distributions for Deep Learning Classification. And so it's this idea that, generally in deep learning you have discrete classes, discrete classification, and you have regression, which is sort of a continuous prediction. This is actually ordinal, so it's discrete but ordered. And some examples of this is like stages of cancer, movie ratings, age prediction if the age is discretized. And so, we have this example here where you actually have three probability distributions, and all three of these so orange is the ground truth, and under a one-hot encoding scheme, they actually all have the same cross-entropy loss. However, some distributions make more sense than others. Like, this one doesn't really make sense because you're saying it's most likely she's an adult, it's second most likely she's a baby, and then third most likely she's a teen. So it doesn't really make sense, right? And so under a one-hot encoding scheme, you can have these problems in a low data regime. So in this case, this is actually the one that makes sense because she's the most likely, and then as you kind of go to the left, it tapers off, and as it goes to the right, it tapers off. So that's this notion of a unimodal distribution. And so we can actually enforce this really easily, right? If you look here, this is actually the PMF of a Poisson distribution. And so Poisson is actually unimodal in the screen. And so if we, so this is the PMF, but if we take the log of it, we get this. And if we make our neural network predict this, which is here, so here lambda is f of x, if we have the neural network predict lambda, we're going to sort of copy it k times. We're going to evaluate the probability mass function for the k different classes. And I mean, in the case of Poisson, you don't have to do this for binomial, but in Poisson, you have to normalize at the end. So when you do that, you actually end up having a probability distribution. You still train it with the cross entropy loss, but it's actually ordinal. It's unimodal. And so in this case here, these are some faces we looked at in the validation set, and this is the sort of the cross entropy, just the baseline. And you can see, I mean, it's not unimodal, but we make it unimodal. Same here, this is not unimodal, this is kind of weird, you got something like that, but then we fix it. And for this beautiful lady here, same thing, it's kind of weird, right? But then we fix it. So all of these are perfectly unimodal, and this is important for two reasons. One is interpretability. The probability distributions make more sense. And the second thing is actually, we've shown empirically that if you're evaluating things like ordinal kappa or top K accuracy, this can actually give you some boosts. So we saw this for one of our data sets, and for the other one, wasn't so promising, but in general, it was good. So yeah, and just before I finish, Da Costa and his colleagues in 2007 had actually, they actually did this 10 years ago. They did it in a classical machine learning context, but we did some things different, but if you do like this work, you should definitely check their work out. They have some nice theory stuff in there, and they also look at non-parametric ways to enforce the ordinality constraint. So yeah.